Hello, my name is John Zeta 180C. Today I will be presenting a paper on the VHF UHF transponder for the Kletskous Cubesat project. This is the first time that I've presented at a conference something about this due to my unavailability of being working in Saudi Arabia currently. I hope it's beneficial to the amateur community, and any support is appreciated. Thank you. Okay, let's start. The main specifications for this transponder is, of course, UHF up and VHF down. We're aiming for about 120 dBs of gain. That is equivalent to a minus 100 dBm signal at the satellite, which will give a 20 dBm output on VHF. That's about 100 milliwatt or even more. The output power we're aiming for more than 200 milliwatt, which is 23 dBm. We're going to try and keep the DC power consumption below 1 watt, which will probably be very difficult due to measurements that has been done. We would like to have AGC so that as the signal gets stronger, the output power stays constant. This board also contains the telecommand receiver and the telemetry transmitter. So next we will be looking at the link budget. First we start off with the uplink budget. At the horizon, you've got about 152 dBs of loss, which is for a satellite in a 600 kilometer orbit. So at the horizon, the distance is 4 times the satellite orbit. Right above us, this lowers to about 140 dBs, which is a 12 dB improvement. We get a 6 dB improvement for ever halving the distance between the transmitter and the receiver. So if we transmit 5 watt, which is 57 dBm, into a nice Yagi of 10 dB gain, and we will get about minus 105 dBm at the satellite. Either satellite will have about 0 dBi antennas, omnidirectional antennas. This will, of course, improve to minus 93 dBm when the satellite is right above us. Now, if we move over to the downlink, VHF downlink link budget, everything, of course, will improve with 6 dB because we are at 4 times lower the frequency. So for the satellite that transmit 23 dBm into a 0 dBi antenna that we are aiming for, we will get about minus 113 dBm at the ground after a nice Yagi 10 dB receive antenna. Again, this will improve to minus 101 dBm right above us. Depending on the power available on the satellite, we will be able to increase the transmit power from 200 milliwatt maybe up to 2 watts, as this will be configurable. Next we will be looking at the block diagram of the initial design, how we wanted to distribute the gain, and I will go through the block diagram and show you also on the PC board where the parts were. We tried to take a modular approach to try and make it as simple as possible without using too much tuning. So we, at the VHF UHF input, we first have got a SAW bandpass filter, which is situated here with this MMCX connector. Just behind it you can see the small SAW filter. After it, we've got our first LNA stage that sets the noise figure of the transponder. We're using a MAX 2640. That's that part there with the power supply, input, output. Then it will go into another bandpass filter, another SAW filter, And after the SAW filter, we've got a splitter to split the signal for the transponder use and for the telecommand receiver. So that is this part here. There's the SAW filter. We will have the splitter here, and then we've got the next stage amplifier after the splitter, which is just extra 15 dBs of gain given by this amplifier. And then again, after the amplifier, I've put in another bandpass filter stage just to make sure that we don't get any funny oscillations. Our biggest problem, of course, with receiving at UHF and transmitting at VHF is that the third harmonic falls very close to the receiving band, so it's very difficult to get isolations at, therefore using so many filters. The next stage is the down converter mixer. So this is the last SAW filter, and then we go into the active down converter mixer that's driven by ADF 4350 local oscillator IC, full-on IC that contains the VCO and everything, just needs a reference. And then we get our first filtering at the IF stage, 45 megahertz, 50 kilohertz bandwidth filter, just after the down conversion stage. Then we get our AGC amplifier, that gives us another 60 dBs of variable gain, which will also be controlled to control the AGC, automatic gain control, on the transponder. After that, I've got made provision for another surface mount IF filter. That's just after the AGC IFM, and then it will go into the uplink mixer, which is again driven by ADF local oscillator IC. I'm using a passive mini circuits mixer because I've used it a lot in the past and it works very nicely. On this design, you can see I made provision for a clear transformer because these AGC amplifiers have got very high input and output impedance. I wanted to transform that, but that gave me some oscillation, so I bypassed that. Then after the uplink mixer, we have got another filter which is mounted at the bottom. That's again another SAW filter that I found here. It's this component that's been used, I think, for Orbcom satellites, which fits very nicely with our frequency range. Then I've got the combiner that combines the telemetry transmitter. So this will be the telemetry transmitter. Of course, that's the telecommand receiver. So the telemetry transmitter, after the splitter here, or combiner here, you can either get the transponder signal or the transmitter signal, both being amplified by another gain stage. The driver just before the power amplifier, and then I've put in another bandpass filter. I was very worried about oscillations and so on. On this one you can see it's been bypassed, and then originally I wanted to put in a 10 dB FET amplifier, but I rather opted to use this 8 volt handheld VHF 8 watt power module that's just been driven now at much lower VCC of 5 volts. And then it goes into the low pass filter to, of course, attenuate the harmonic. So there's the power amplifier, the low pass filter, and then I've got a measuring device to measure the output power. You see the AGC here is actually implemented using this final stage, which I found wouldn't be working if we use our transmitter. I'm not 100% sure if the transmitter will be used together with the transponder function. So the base will be actually to put the detector rather before that transmitter, and of course the feedback to change the AGC gain. So there's the detector IC, so I can measure the power, and then there's the output. I've got a microcontroller on the back side of the PC port. There's a DCXO 10 MHz that It's the reference for everything, the microcontroller, transmitters, receivers, and the local oscillators. Yes, so that's the block diagram.